Ever try to solve a puzzle and just as you get close to the answer, it literally slips right through your fingers? Well, we've spent a lot of time guessing limits from graphs and tables lately, but today that guessing game stops. Welcome to today's explainer, where we are going to unmask the absolute rules for calculating limits algebraically. No more estimating, just absolute, undeniable certainty.
I mean, you know what I'm talking about, right? Have you ever been totally frustrated by squinting at tiny decimals or zooming in on a table of values only to hit a complete dead end? Well, you can officially leave those rough estimates in the past. For all you future doctors, engineers, and real-world problem solvers tuning in, we are officially transitioning to a system of absolute mathematical truth.
Okay, let's dive into this. I am incredibly excited to welcome you to this brand new mathematical adventure with Mr. Math. So grab your notes and lock in your focus because we are about to decode the very foundation of calculus together. Let's go.
Section 1. The Limit Toolbox. James Stewart's Limit Laws.
So, to dismantle complex equations, the legendary mathematician James Stewart hands us a set of fundamental tools known as the limit laws. Honestly, you can think of the mathematical limit as just a really generous guy. It distributes smoothly and fairly across almost everything. We've got the sum law and difference law, which basically mean the limit of a sum is just the sum of the limits. Easy. The same exact logic goes for multiplication with the product law. And for division, the quotient law says the limit of a quotient is the quotient of the limits, with just one absolute, unbreakable rule. The limit of the denominator absolutely cannot be zero. But generally, if you have two functions, just take the limit of each one and combine them. It is literally that straightforward.
Section 2. The Direct Substitution Shortcut. Fast-tracking polite functions.
Now, I know what you're thinking. You're wondering, is there a faster route to all this? Oh, absolutely. Let me introduce you to the magic of the shortcut. This is called the Direct Substitution Property. If the function you're looking at is a polynomial or a rational function, and the number you are approaching is actually in its domain, please do not waste your time distributing limits step by step. Just plug the number right in. For these nice, polite, continuous functions, the limit as x approaches a is literally just the value of the function at a.
And this brilliantly illustrates exactly what I mean. We have the limit of 2x squared minus 3x plus 4 as x approaches 5. Instead of applying the limit laws one by one like a robot, we use our shortcut. We just substitute 5 for every x. So 2 times 25 is 50, minus 15 plus 4, giving us an instant, perfectly accurate answer of 39. Beautiful, right?
But wait, stop right there. Pause the explainer for just a second and think about this with me. What happens if you use our amazing shortcut? You plug the number in, and your result is exactly 0 divided by 0. Does that mean the limit just doesn't exist? Or is the function trying to tell you something else? Is it whispering, hey, look a little closer?
Section 3. The 0 over 0 Rescue Plan. Algebraic Rescue.
So when you hit 0 over 0, you have officially entered what we call an indeterminate form. Basically, it's a math crisis. But here is the secret. The limit actually exists. It's just hiding behind a mathematical conflict between the numerator and the denominator. And this is exactly where we deploy our escape route. By using algebra, specifically techniques like factoring, we can totally bypass the trap, cancel out the hidden problem, and reveal the true limit.
Now, what's really interesting about this slide is how elegantly this rescue plan actually works. Look at step 1. Direct substitution gives us 0 over 0, a total dead end. So moving to step 2, we factor the numerator. It's a difference of squares, so it becomes x minus 1 times x plus 1. Step 3 is where the magic happens. The problematic x minus 1 terms cancel each other out perfectly, leaving us with just x plus 1. For step 4, we bring back our direct substitution shortcut, plug in the 1, and beautifully unmask the hidden limit. It's 2. See how easily we bypass that trap?
I should definitely mention that factoring isn't your only weapon here. If you face a really stubborn limit that involves square roots and it hands you a 0 over 0 result, you'll want to use a trick called rationalizing. By multiplying by the conjugate radical, you clear out the root and expose the hidden limit, exactly like factoring does. It is a super powerful backup plan.
Section 4. The Squeeze Theorem. The Mathematical Sandwich.
All right, let's move to our final conceptual tool. Because sometimes functions are so messy that neither direct substitution nor our algebraic rescue plans will work, for those absolute nightmares, we rely on the squeeze theorem. Imagine you have a highly unpredictable function, f of x. If you can trap it, or sandwich it, between two predictable functions, g of x on the bottom and h of x on the top, you are back in complete control. Think about it. If the bread on top and the bread on the bottom are moving to the exact same destination, let's call it L, then the messy meat trapped in the middle has absolutely nowhere else to go. It is forced to approach that exact same limit. It's a brilliant, airtight way to trap a limit into revealing itself.
Section 5. The final challenge. The final boss.
Okay, you have the limit laws, the substitution shortcut, and the algebraic rescue plans. It is time to test your skills. Look closely at the challenge on the screen. We want the limit as h approaches 0 of the quantity 3 plus h squared minus 9 all over h. So the crucial point is this. If you try direct substitution right now, you will get our old nemesis 0 over 0. So I dare you, all the true future engineers and problem solvers watching, to use your algebraic expanding and factoring skills to break this down. Expand that numerator, simplify it, cancel what you can, and unmask the true limit. Do you think you can solve it?
Because if you can, you've learned how to completely dominate limits using absolute algebraic certainty. You are officially masters of the limit toolbox. Don't forget to drop your final answer to the challenge in the comments below. But before you go, I want you to think about this. If we can now perfectly calculate the infinitely small, what happens when we start adding all those infinitely small pieces together? That right there is the true secret of calculus, and it's a mystery we'll uncover in our next adventure. Support this explainer with a like so you don't miss out, and I'll see you next time on Mr. Math.